Okay, let's get started. Hi, so as mentioned, my name is Tomo Gabel. I work for a company called Wix, which is not the point here, so let's get right to it. What I'm going to be sharing with you over the next 25 to 30 minutes is some historical context and an assertion about the state of the software industry. So to put things in perspective, who here is a software engineer? Please raise and keep your hand. Okay, who's been doing that for 5 years or less? You can drop your hands. Who's been doing that for 10 years? 20 years. Okay, we have like one or two. Good on you. Right, so I want to take you back through the looking glass about 20 or so years ago. So we're talking like 1994, 1995. And the state of the market was basically that C and C++ ruled the day. Okay, we're talking 20% market share between the two of these. The next languages in terms of popularity are Lisp and probably COBOL or something, but they're lagging way, way, way behind. And 1995 also saw the first release of Java, actually the very tail end of 1994. So looking back 20 years, what has changed? So nowadays, C, C++, and Java are kind of neck and neck. JavaScript is definitely gaining significant market share, although it's kind of used in different spaces. Some of the sort of underlying principles of Java and the Java virtual machine are pretty much ubiquitous nowadays. So pretty much any language that you might be using today, be it Python or Ruby or JavaScript or Java or C# or any of the other languages are basically based on virtual machines. They're garbage collected, and typically they're object-oriented. So let's take a quick look and give a bit of historical context. Virtual machines, popularized with Java in 1995, are not a new idea. So 50 years ago, a new language for building compilers was put on the market called BCPL. And what was unusual about it is the BCPL compiler had this division that we all know and love for modern compilers into a language front end and an architecture back end. That was the first compiler to do that. 10 years later, UCSD P system, or UCSD Pascal as it's called, gained a bit of mainstream notoriety, and it took the idea to the next level. So instead of just having the compiler read in BCPL or Pascal or whatnot and emit an intermediate representation to be subsequently transformed into native code, what they actually did was they did that on the fly, right? The canonical representation for code was O code, the intermediate representation for BCPL, or P code for UCSD Pascal. So it just took the idea to the next level. Almost 20 years later, we have Java. And Java was the first language to kind of popularize this idea of a virtual machine that actually takes a representation of your code, Java bytecode in that case. If you're coming from a .NET background, you might have CIL or BCPL, or whatever, MSIL as it used to be called. And it transforms that on the fly to the target architecture. So those ideas are not new. And nowadays, pretty much any language you might care to use, any technology that you might care to use, is sort of based on these ideas that are literally 50 years old, right? So to give another couple examples, let's take a look at garbage collection. Garbage collection is not a new idea either. It was actually first formalized with the Lisp paper by McCarthy in 1960, right? So we're talking 57 years ago. And he basically proposed this notion of garbage collection as we know it today, right? Not much has changed. It's the same underlying principle. A lot of the research about garbage collection was done in the 70s. So Cheney's algorithm, which is the copy collector, mark and sweep, all of the things that we know from modern garbage collected languages aren't new either. Most of the research is 40 years old. Once again, Java popularized this notion of a fully garbage collected mainstream language back in 1994. And fast forward about 20 years, I should have updated the slides to say 2017, but the same principle holds, right? All of the languages that we use today, unless they are designed not to be garbage collected, and modern languages hardly ever do that. It's basically Rust, right? Unless they're specifically designed not to have that, all of them are garbage collected. So, it's also, we're talking 50 years between conception and mainstream adoption. Final example, object-oriented programming. Who here does not do object-oriented programming? I see maybe 2 hands. I'm guessing you're doing functional programming, but that's fine. The point is that it's ubiquitous. And everything that we know and love from object-oriented programming, the 3 tenets, encapsulation, polymorphism, inheritance, all of these things are present pretty much as we know them in a 50-year-old language called Simula 67. The term object-oriented programming actually comes from, was actually coined by Alan Kay in 1980 in reference to the Smalltalk 80 language. But it was sort of made mainstream by C++ in 1983, and even that took almost a decade to actually, kind of convert most C developers into C++ developers. And nowadays, almost every programming language that you might use is object-oriented. Still, we're talking 50 years. So, to make the point, advances coming out of research, coming out of academia, no matter how appropriate, no matter how advanced, no matter how relevant, take decades to come to fruition in the mainstream software development market. And pretty much everything that we perceive as new-ish today actually hails back, several decades to research in the 60s and 70s and sometimes 80s. So, what causes things? What causes paradigms to be adopted in the mainstream? Now, there's a lot of different theories about that. My kind of hypothesis is that this is the result of market pressure. Right, so what we have here is a nice graph that charts the sales, the overall total volume of computers on the market. And by computers, I mean, everything from mainframes back in the 70s to PCs to smartphones, tablets, right? Everything you'd basically call a computer. And you can see that up until about 2014, at which point it becomes a projection of what the market will look like, you can see pretty steady growth. This is in millions of units. Now, if we look at this graph, we can see interesting things start to happen. We can chart that very early, very late 70s, very early 80s, we can see that the market is very, very small, right? But it was growing. PCs started making their way into the mainstream, into homes, into offices, and software development back then was way, way, way harder than it is now. And the demand for software outstripped and outpaced supply by a ridiculous margin. Okay, there was much more demand for software than the industry could actually produce. And that caused a number of paradigm shifts in how software development is done on a daily basis. Back in the early 80s, that would include things like structured programming. So instead of using go-tos, you might use subroutines, procedures, functions, etc. You'd have module systems. You'd have dynamic memory allocation. So it turns out that free and malloc weren't really a thing until the early 80s. I mean, they were known, but weren't really in widespread use. And just adopting these kind of 3 paradigms allowed so many more software engineers to come onto the market. People who are not necessarily as passionate or not as disciplined about their everyday software development were suddenly able to build software, working business software. Right? So that allowed the market to grow. And you can see, starting in around 1980, huge growth in the curve. Right? The rate at which the market was growing suddenly got unlocked and started climbing up. A second kind of inflection point was around 1995, which is roughly when Java came out. Java introduced into the mainstream these notions of garbage collection, object-oriented programming, virtual machines. JIT wasn't really a thing back then. It still took a few more years for Hotspot to kind of gain market share. But just these made software development, like everyday kind of business, enterprise software development, so much easier that the market just exploded. Right? Suddenly, being a software engineer became a thing. It became a viable career path. It became a very desirable career path because it pays very well. And Java was one of the technologies that kind of paved the way for the market to grow. And now, finally, we are roughly here. And if you look at the graph, this graph is a projection, right? They didn't actually know, they just made extrapolations based on recent data to sort of try and chart where the market is going. And you can see that the growth rate has almost flattened. And the reason for that is, in my opinion, that we're once again at this point, at this inflection point, where the demand for software outstrips supply by a significant margin. Right? We need more software developers, and for that to happen, we actually need software development to be easier. Now, what's holding us back, right? If I'm making the assertion that it's hard for new people to come into software development today and we need a new set of tools, I need to explain what has changed, right? We've had 20 very good years. Now what's different now? Well, the market has changed significantly. So whereas 10 or 20 years ago, the norm would be shrink-wrapped software, basically you'd go into a shop, you'd buy a copy of Windows or your favorite computer game. Nowadays, no one does that. When was the last time you actually went into a shop to buy a piece of software, right? Digital distribution is one of the two kind of favorite ways of distributing software nowadays, but I would argue that SaaS is actually the norm, right? For email, you might use Gmail or Hotmail or Outlook, or whatever the hell you want, right? But fundamentally, you consume services through web-based applications that you don't run at all. Your computer, other than the browser, is not involved, so that's the norm now. Time to market shortened considerably. 20 years ago, a 3 or 6 or 12 months product cycle was not unheard of. It was pretty common even, right? Nowadays, software that doesn't get updated for 3 months is dead software. It's never gonna see mainstream adoption. The time to delivery has shortened from years and months to weeks, days, hours, minutes even. Right? Continuous delivery is sort of the norm for modern day software houses. So that is a huge radical shift in how we build our software. Also, latency. Latency has dropped significantly. Whereas 10 years ago, it would have been fine for a website to take 5 seconds to load. Nowadays, if a website takes more than a second, the first thing you do is assume something went wrong and retry. And the second thing you do is close the browser because this site is slow and you don't feel like waiting. Right? So latency requirements became way stricter. And finally, availability has changed dramatically. So whereas 10, 15 years ago, it would have been perfectly acceptable to take down your system overnight to run a batch job or a backup or a cleanup process, you can't do that anymore. Because if you take your system down in the middle of the night, your customers on the other side of the world are not going to be able to get their work done. So global availability and subsequently desirable high availability are now the norm as well. So all of these things just dramatically changed over the last 15 years, and they require new ways of building software. Next, the free lunch is over. So this is a very well-known landmark article from Dr. Dobbs' journal back in 2005, and it made the assertion that CPUs basically are not getting a lot faster and are not going to get a lot faster. Basically, it made the assertion that Moore's law is no longer in effect. It was never a law to begin with, sort of tongue-in-cheek, but it's no longer in effect. CPUs are not getting significantly faster, but we are getting more of them. So whereas 15 years ago, almost all PCs would have just one monolithic single-core CPU, nowadays you have in your home computer, hell, on your phone, you have 4 or 6 or 8 core CPUs. Right? And that's just mainstream consumer market. Actual servers these days can come with 64, 128 cores. Right? We get more cores. We get more threads per core. We get more sockets, more nodes, more clusters, more data centers to house these clusters. Everything is becoming more parallel instead of just playing faster. Concurrency. Concurrency is the new kid on the block. Everything has to do with concurrency. If you want to do modern day software development, you want to do computation, you're going to have to deal with concurrency. Finally, data sets are getting bigger. So whereas if you went to a software conference like this one 15 years ago and you spoke to anyone and they told you that their data set is 2 terabytes in size, 2 terabytes was a huge data set 15 years ago. Nowadays it's trivial, right? Everyone in this room either has or can have data sets that are terabytes in size. Petabyte is the new terabyte. So the need for not only the ability to actually store this data, but actually run computations on that scale of data, batch jobs, search engine indexing, if you think like Google or Bing, right? All of these things are becoming commonplace, becoming necessary to do modern day software development, but they just didn't exist 15 years ago. Also, if you needed like huge scale storage and large scale performance out of that storage 15 years ago, you would have bought like an EMC or a NetApp cabinet with a whole bunch of hard drives, specialized hardware. You would have connected it with fiber channels. All of these things that you do to get high performance and high throughput 15 years ago no longer apply today, because today, ideally, you're running on someone else's hardware. You're running in a cloud somewhere. You're running on AWS. You're running on GCP. Whatever the case, you can't get these things installed for you because it's commoditized, right? So this is no longer even a possibility. Tying all of this together, what this means is that if so many things have changed and so much kind of new types of software, new demands are made on software, then we need new abstractions in order to enable building that software on the cheap. We want to enable the market to grow. We want more people to come in and be able to develop mainline business software on a day-to-day basis without having to worry about the underlying complexities. We need new abstractions. So what is a new abstraction? We have three desirable attributes. If today's systems are highly available and reliable, by which I mean we need something like 3 nines or 5 nines of availability, depending on context. No one needs 5 nines, but never mind that if you're not Google. Tomorrow's abstraction must encourage correct code, right? We need to adopt programming paradigms, programming abstractions that encourage us to do the right thing. Systems are becoming more complex, right? Software systems do more nowadays. 20 years ago, you would have been very happy with an inventory management program running on a PC in the back of your office. Nowadays, you need that to be highly available. It's generally SaaS. It deals with more data. It's more complex. Complex systems mean bigger code base. Bigger code bases mean more code, and that means more bugs. So ideally, we want abstractions that enable us to write far less code, and we want that code to be correct by design. So we want our programming tools to actually encourage us not to make mistakes and to write less code in order to get our work done. What this means is that we need to invert the way we write code. And you can actually see that happening in modern day programming languages, even traditional ones like Java. And by inverting from, and by switching from control flow to data flow, what I'm actually talking about is our code should reflect the what we're trying to do as opposed to the how we're trying to do it. So to give you a quick example, here's a very stupid artificial bit of code, right? It's a function that takes in Java. I'm sorry if any of you don't speak Java, but the underlying principles are the same in any language, right? We have a function that takes in a list of people and it filters out the adults. Right? So it builds a new array list, an intermediate data structure to hold like our interesting elements. It iterates over the list of people. If it runs a predicate, if the predicate matches, like if the person is an adult, it just gets added to the outbound array list, and then we return that. Right? This is a very stupid piece of code. That's not the point. But it describes the how. This is all implementation details. Nothing in this code gives you a very, very good idea right off the bat what it's intended to do. Contrary-wise, with Java 8, we get the Streams API. So if you rewrite this with the Streams API, you actually get code that looks roughly the same. You take your input list, you convert it into a stream, you filter on it based on this predicate where age has to be greater than 18, and then you collect that to a list. So these two pieces of code are not that dissimilar. We haven't even saved all that much code, right? This is roughly the same volume of code, except this version of the code reflects the intent of the software developer. It lets me focus on my business requirements, not on the implementation details. I don't need to pick an intermediate structure. I don't need to deal with iteration. I express my intent in very clear terms. Take an input list, filter it, collect to a resulting list, right? This has several desirable properties. First of all, it lets me focus on the things that are interesting to me, not on the accidental complexity of writing my loop statements. It reduces this accidental complexity, and crucially, it decouples intent from execution. Right? I express declaratively what it is I mean to do, and I let the software, the underlying platform, deal with the details of how that actually gets done. Right? And that is crucial because this decoupling allows me to deal with my business logic and allows people who are much more passionate about data structure and distribution and optimization to deal with the low-level details of how to execute my plan in the most efficient way possible. And that turns out to be a very, very good way of doing things. Next, today's systems are highly concurrent. So tomorrow's abstractions must encourage immutability. Why is that? Immutable code, does anyone here not know what immutability is, by the way? Okay, I don't see any hands in the air. I apologize if I missed you. So basically, if you deal with immutable data, that means you're inherently thread safe. You don't have to synchronize on it. You don't have to lock. You just give it away, and everyone is happy, right? There is no way to make a mistake there. Also, it's referentially transparent, which means that the compiler is at liberty, whatever compiler phase we're talking about, whether the ahead-of-time compiler or the jitter, has a lot more liberty to make optimizations to your code. So actually, the resulting execution tends to be significantly faster than what you would have with shared mutable state. Finally, it's way easier to reason about. Suddenly, if you don't have to worry about threading issues and locks, your code becomes smaller and simpler and easier to read and has less mistakes in it. Right? When was the last time you've written heavily threaded code, came back to it 6 months later, and then had to spend several hours kind of mentally sifting through the code and figuring out, what was the intent in the first place? What is all this threading code doing in the middle of my nice, lean business logic? Right? It just makes the code easier to deal with. So that has only benefits nowadays. Finally, if today's systems need to be horizontally scalable, because we're talking commodity hardware, larger data sets, right? The abstractions that we pick must simplify workload distribution, right? If we have more and more CPUs, more cores, more servers, we need abstractions to make it easier to take advantage of this inherent parallelism in our computing platform. So distribution, right? Fundamentally, distributed computing is you have some sort of core computation that you care about. You split it out of your kind of mainline business logic. You send it to a bunch of cores, to a bunch of servers. You get back a response, profit. Fundamentally, that is all distribution is, right? This is actually kind of hard to do in practice because you need these three attributes to whatever programming paradigm you work in for that to work. We need behaviors data because fundamentally we're taking a bit of computation and we're sending it to a remote node for execution. So we need to treat behavior as its own data so we can send it over the wire. We need to minimize side effects because side effects are sort of the enemies of concurrent code. And we need high-performance frameworks to actually enable us to do this. Now, 15 years ago, we had none of these things, right? 15 years ago, writing a fully distributed system was actually very, very, very hard. Nowadays, we have a lot of this. So behavior is data, is lambdas, right? Whatever language you use, fundamentally, when you write a lambda or a closure, whatever you want to call it, you are basically describing behavior that can be passed around freely as data. Side effects. Well, if you have immutability, then you have just eliminated the vast majority of side effects that you might care about. State manipulation is the most common of side effects. If you manage to avoid doing that, then, well, sure, you still might have side effects, but basically most of the significant kind of swath of the problem is eliminated. And with high-performance networks, you have a whole bunch of these that you just didn't have even 5 years ago. Spark was not a thing 5 years ago. You had Hadoop, which was also an order of magnitude better than anything you had before that. But there's been a lot of progression in high-performance distributed system frameworks that allow you to actually build these systems without banging your head against the wall. So I assert that elements from functional programming are making their way into the mainstream, and it's a good thing. You will note that I'm not actually advocating for you to learn a functional style programming language tomorrow. I don't personally adhere to the pure functional style, but I would argue that functional programming, at least conceptually, as a programming paradigm, has a lot of these really, really desirable properties. Functional code is fundamentally data flow oriented because there is no state. It's immutable because it is by design, and it's easy to distribute because fundamentally you're dealing with functions as data, right? So all of these attributes are really, really desirable because they make it much easier to build correct, high performance, highly scalable, highly available, resilient systems. And you will note that these properties of functional programming are actually making their way into mainstream programming languages today. And over the last 10 years, it's been doing that. So, inverting from control flow to data flow, you can see with LINQ and C#. You can see with Lambdas and the Streams API in Java, right? Any modern software programming language actually has some sort of behavior-based collections framework, right? So that is a good thing. Immutability actually has not made its way into mainstream programming languages yet. But if you look at kind of the more modern ones, like Rust, like Scala, Go I'm not as familiar with, unfortunately, so I can't really talk about it. But you look at Scala as one example, it encourages immutability. You actually have to be explicit about the things that you want to be mutable. And just that makes it a lot harder to screw up. It protects you. It encourages you to do the right thing out of the box. All right, so a lot of these things are making their way slowly into mainstream programming, and you should probably take a closer look at these features, at these properties, at these other languages that originated these features, because these paradigms actually enable you to be a lot more productive, and it enables the market to grow. Suddenly it becomes a lot easier to tackle the problems that we have today, which means more people can come in and do the work, which means the market can grow again. And with that, if there are no questions, I am done.